All right, so we've been talking about stoichiometry, and now we're going to be focusing on balancing our chemical equations. I'm going to presume that most of you have done this before, and so I'll probably go a little on the fast side, so I apologize for that ahead of time. If you need to, obviously, since it's a recording, you can always pause it, go back, and watch it a couple times. So if you are struggling with balancing, feel free to do that. Also, if you are struggling with balancing, make sure you get a hold of me, and we can get together on Zoom or something along those lines, or an office hour, and I will go through it a little slower with you individually. So balanced chemical equations, obviously it's going to be a useful tool for problem solving. You're going to have to be able to do that. So it's going to be able to tell you how much of your reactants and products are going to be there on mole quantities, right? So all the atoms present in the reactants have to be present in the products. And then of course we know the coefficients are going to be multipliers that are going to be used to actually balance the equation. So it's looked at as a two-step process. First, you write an unbalanced equation. A lot of times we'll call that a skeleton equation. So you'll write out the skeleton equation, and that's telling you what's actually going to happen. Sodium is reacting with water. It's producing NaOH, sodium hydroxide, and oh my gosh, H2 gas. Losing my mind a little bit. So that would be our skeleton equation. Once we have the products and the reactants listed out, the plus signs and the arrows are all in there, the second step is to adjust with the coefficients. So that's where we're going to make sure that we have one sodium on each side. We're going to make sure we have two hydrogens on both sides. We're going to make sure we have the right number of oxygens. All right, so some guidelines then. Start balancing with the most complicated formula first. So elements, particularly H2 and O2, should be left until the end. And that's because they're by themselves, but in pairs. And we have a doubling trick, and we'll show you that as well. You can balance atoms that appear in only two formulas, one as a reactant and the other as a product. Leave elements that appear in three or more formulas until later. And that's because they break apart a certain way. Balance as a group those polyatomic ions that appear unchanged on both sides of the arrow. So if we have nitrate on both sides, balance it as nitrate, not nitrogen and oxygen. Now, if you don't catch that and you do balance it as nitrogen and oxygen, it still has to work out. All right, so that's no big deal. Just it takes you a little bit longer because you have more things you have to take care of. So balancing equations, you can use the inspection method where you write the unbalanced equation. So here we have zinc reacting with HCl to produce zinc chloride and hydrogen. Next we're going to do is adjust our coefficients. Since we know we have ZnCl2 has two chlorines, right, on the product side, then we know we're going to need two HCl in the beginning. Now we'll just check to see if it's balanced, and of course it is, right? So that's balancing by inspection. You can do them pretty fast. All right, so silver nitrate plus sodium phosphate producing silver phosphate and sodium nitrate. First, we'll count our atoms. So a little more complicated here. So on the reactant side, we have one silver. On the product side, we have three silver, three sodium, one sodium, and now we'll adjust the coefficients of both the nitrates to 3, right? Now we can check the polyatomic ions just to make sure they worked out. We have 3 nitrates on one side, 3 nitrates on the other, one phosphate, one phosphate. So once again, the equation is balanced. All right, so try balancing this one by inspection. First thing you're going to do is assume there's a 1 in front of the C3H8. So you have 3 carbons, which means we need 3 carbons on this side. We have 8 hydrogens, which means we're going to need 2 times 4, 8 hydrogens on that side. So we're going to start with a 1 there. We're going to put a 3 and a 4 in to those two. Right, so now if we do our oxygens on this side, we have 1 oxygen, 3 times 2, plus 4 times 1. And so of course, that's going to give us 6 plus 4 is 10, which means we need 10 on this side. We know that the oxygen's coming in pairs, so we're going to need 5 of them. And that would be our balanced chemical equation. All right, so balance each of the following equations. What are the coefficients in front of each compound? All right, so I guess I'll pause in between each one, so that way you can work on it and then just start the video again. All right, so there was your pause. All right, so if we're going to do this by inspection, we can see we have 1 barium. Let me fix this real quick here. There. So we have 1 barium, 1 barium, 2 hydroxides here, only 1 hydroxide over there. 2 sodiums, 1 sodium, 1 sulfate, 1 sulfate. So obviously I need 2 hydroxides, but everything else looks like it's going to be evened up. And so there we have 1, 1, 1, 2. That gives me 2 sodiums, 2 sodiums, 2 hydroxides, and 2 hydroxides. All right, so I'll give another pause for the second one. And this time we have 1 potassium, 1 potassium, 1 chlorine, 1 chlorine, 3 oxygen, 2 oxygen. And so right away, the only way I'm going to get those two to match up is going to be 3 to 2, right? So the common factor here being 6. So we'll put a 3 in front of the O2. And then we're going to put a 2 in front of the KClO3. Now once I've done that, I'm going to have 2 Ks and 2 Cls. No big deal. We'll just put a 2 in front of the KCl as well. And of course that works out. All right, a little pause for the last one. Okay, so now we have H3PO4, we have BaOH2, Ba3PO42. So what I'm going to do is, since I have 3 here, I'm going to go ahead and put a 3 right there, because I have 3 bariums over here, so I'm going to put 3 bariums over there. Here we have 2 phosphates, so I'm going to go ahead and put a 2 in front of my H3PO4. So now I have 2 phosphates. So we have 2 phosphates, we have 3 bariums. This is going to give me 6 hydrogen, and this is going to give me 6 hydroxides, which means if I put those together, I'm going to get 6 waters. All right, so remember, we can always think of water as HOH. So now we can see that hydroxide component coming from the base, and we can see the acid component giving us this just straight hydrogen. And so there we see that one, 2, 3, 1, 6. So hopefully you did well with those, right? Now, using those balanced equations. So again, I went through kind of fast for balancing equations, but I want to get to the important stuff of the stoichiometry. The critical link between substances involved in chemical reactions. So this is going to give us our relationship that's going to allow us to react, or I should say not react, but allow us to calculate back and forth between our reactants and our products. So the numeric coefficient is telling us what the mole ratio is. So if it's going to go, if I go back and look at this, instead of just balancing, for every 2 phosphates, I'm going to need 3 barium hydroxides. And we saw how that worked in the molecular sense, and it's going to be the same sort of idea, except now between 2 different compounds. So how many individual particles are going to be needed in the reaction on the microscopic level? How many moles are going to be necessary on the macroscopic level? So your stoichiometric ratios, consider the reaction. So we have nitrogen plus hydrogen is going to give us ammonia. A couple different ways we could read this. We could say when 1 mole of nitrogen reacts with 3 moles of hydrogen, 2 moles of ammonia are formed. Right? We could look at the molar relationships. So we have 1 mole of nitrogen is going to give us 2 moles of ammonia, and that's based on those coefficients. We could say we have 3 moles of hydrogen is going to give us 2 moles of ammonia. Or we could look at 1 mole of nitrogen is going to need 3 moles of hydrogen. So again, we have the same sort of molar relationships between these as we had with the compounds and looking at the quantity in the compound itself. All right, so there's our reaction. We could also read it as when 1 molecule of nitrogen reacts with 3 molecules of hydrogen, 2 molecules of ammonia are formed. So we could do molecular relationships as well. Now again, these won't be as productive as the molar relationships, because when we do reactions, we're going to be doing reactions in terms of moles. We're not going to be doing them in terms of molecules. All right, so stoichiometry then, if we have a mass balance of all the formulas involved in our chemical reactions, so what we can do is start to use those conversions to look at the mass that's involved. Now again, you can always use your dimensional analysis, right? The things you'll need to know, the equalities to make the conversion factors, that's the balancing of your reaction. The steps to go from the starting units to the desired units. And it's going to be a 3-step process once again. So for that same reaction, how many moles of nitrogen are going to be used when 2.3 moles of ammonia are produced? So once again, we can assemble the tools. We know that 2 moles of ammonia will equal 1 mole of nitrogen. So for every 2 moles of ammonia that we make, we're going to need 1 mole of ammonia. So if we have 2.3 moles of ammonia, how many moles of nitrogen will we need? So we'll start with 2.3 moles of ammonia, and then we'll set it up so that we can cancel those out. moles of ammonia cancels out, leaving us with moles of nitrogen. And of course, 2.3 times 1 divided by 2 will give us 1.2 moles of nitrogen. All right, now again, your questions on your exams are not going to look that simplistic. Hopefully, though, that all made sense, right? Let's see. If 0.575 moles of CO2 are produced by the combustion of propane, C3H8, how many moles of oxygen are consumed? The balanced equation is. Now, the other thing you got to remember is on a test, I probably will not be balancing your equations. So the first thing you're going to have to do is balance that equation. Now, it's already done for us here, but be prepared for that on the test. Sometimes you'll have to balance it before you can do anything else. All right, so here are our options. Give a little pause there, and hopefully you pick D, 0.958. Again, the way we would do it, we have 0.575 moles of CO2 would be how many moles of oxygen? We know that 3 moles of CO2 will produce 5 moles of oxygen after we've balanced it. So 0.575 times 5 divided by 3, and that's where we got our 0.958. All right, let's give it a try again. How many moles of hydrochloric acid are required to completely react with 1.43 moles of iron 2 chloride, according to the reaction below? Now, the other thing you got to be prepared for is I might not even give you the reaction. So here, I might just say how many moles of hydrochloric acid are required to completely react with 1.43 moles of iron 2 chloride. And that'll be it. Now, that won't be for another chapter. So once we get into solutions, we're going to look at predicting products. So remember, everything in chemistry is going to build, and so that's what we're going to be building to. Now, here are our options. So we have 1.43 moles of iron 2 chloride, and we want to know how many moles of hydrochloric acid are going to be required. So hopefully you pick D. We know that 1.43 moles of iron chloride are going to equal how many moles of HCl? And according to our balanced chemical equation, it's going to be 6 to 14. So we'll take our 1.43 times 14, divide by 6, and that should give us 3.34. All right. Now we call these mass to mass conversions. But look, again, it's a 3-step process. We're going to go from mass of A to moles of A. Now, instead of using the chemical formula, we're simply going to use our balanced chemical equation to get moles of B. So before we were using the compound itself and the formula, now we're going to use the entire balanced equation. And then once we have moles of B, same thing, using the periodic table, we'll get grams of B. So again, this is going to be your number one 3-step method you're going to use. We'll use moles of A to get mass of A, mass of A to moles of A, moles to A to moles of B, and then moles of B to mass of B. So you're going to need to use the balanced chemical equation. So write what mass of O2 will react with 96.1 grams of propane gas to form gaseous carbon dioxide and water. So the first thing we need is that balanced chemical equation. We saw that earlier a few slides back. Now what we're going to do is assemble our tools. Well, we know we want to know a 3-step process. So it's going to be 96.1 grams is going to go to moles. So we're going to do grams of propane to moles of propane. From moles of propane, we'll go to moles of oxygen. And from moles of oxygen, we'll go to grams of oxygen. So we know that 1 mole of C3H8 is going to be 44.1 grams. Now that's coming from our periodic table. We know that 1 mole of oxygen is equal to 32 grams, also coming from the periodic table. We know that 1 mole of propane will be requiring 5 moles of oxygen for the reaction. And that's again coming from our balanced chemical equation. So let's look at our conversions then. We're going to start with our 96.1 grams. We're going to convert that into moles. So we're going to use that molar mass from the periodic table. Grams of propane will cancel out. We'll be in moles of propane. Then we're going to use our balanced chemical equation. For every 1 mole of propane, we're going to need 5 moles of O2. So moles of propane will cancel out. Once we're in moles of oxygen, we're going to go to grams of oxygen using our periodic table once again, and then moles of oxygen will cancel out. So we're going to take 96.1, divide by 44.1, multiply by 5, multiply by 32, and that should tell us we need 349 grams of oxygen for this reaction to go. All right. How many grams of Al2O3 are produced when 41.5 grams of aluminum react? So here's our balanced chemical equation. So once again, we did the balancing for us. And there are your possible answers. So I'm going to give you a pause here. Again, try to work these out and then come up with your answer before I actually go through it. That's how you're going to know if you're on the right page or not. So hopefully you came up with A. And now how should you have done this? Well, you're going to start with the 41.5 grams of aluminum. We're going to use our periodic table, get the molar mass from there. Going to cancel out grams of aluminum. We'll be in moles of aluminum. For moles of aluminum, we're going to use our balanced chemical equation. It's going to take 2 moles of aluminum to produce 1 mole of aluminum oxide. So moles will cancel out. And then once again, we'll use our periodic table. 101.96 grams of aluminum oxide is the molar mass. And we can see that the moles of aluminum oxide will cancel out. We run that through our calculator, and that's how we get 78.4 grams. So plenty of practice problems here. Again, feel free to stop and rewind and go through these. Some students will be a little prideful about it. No, don't be prideful. Go through and look at it until you understand what's going on. Nobody's going to know how many times you viewed it. I mean, I guess I could figure that out if I want to, but I'm not going to. So just view it all day long if you need to. But you want to make sure you're understanding how we're getting to where we are. If not, don't hesitate. If you feel yourself starting to struggle a little bit and you need some help, come get it. Do not hesitate and wait till it's too late. All right, how many grams of sodium dichromate are required to produce 24.7 grams of iron 3 chloride from the following reaction? And there are your possible answers. So we're looking for the sodium dichromate based on 24.7 grams. So we're going to start with the 24.7. We're going to convert that to moles. Then we're going to go from moles of iron 3 chloride to moles of sodium dichromate. And then the third step, using our periodic table again, we'll go from moles of sodium dichromate to grams of sodium dichromate. Hopefully you came out with 6.64. So again, we'll start with our mass of iron 3 chloride, divide by 162.2, that's coming from the periodic table, that's our molar mass. Then we're going to divide by 6 because it's a 1 to 6 relationship. We're going to need 6 iron chlorides. We're going to produce 6 iron chlorides from 1 sodium dichromate. And then last but not least, we'll use our molar mass and get the mass of the sodium dichromate. All right, so molecular level of reactions, we're going to take ethylene and water before the reaction. After the reaction, we're going to have ethanol. Okay, so simply showing how we're going to fix things together. So if you didn't realize this, things have to come apart and then get reassembled in order to make our products, and that's sort of how we can think about it. So C2H4 plus H2O goes to C2H5OH. So 3 molecules of ethylene plus 3 molecules of water react to form 3 molecules of ethanol. Okay. Now, what happens if these proportions are not met? So in other words, let's say I have 3 molecules of ethylene and 5 molecules of water. Well, you can see all the ethylene will be consumed, but some of the water will be left over. Right? Hopefully that makes sense. So if I have a balanced chemical equation and everything goes up in the same multiples, then everything will react. But if they don't go up in the same multiples and I have more of one thing than the other, then we're going to get leftover reactant. And that's the gist to one of our last topics here, and that's limiting reactant. So we have 2 topics left. We want to look at limiting reactant, and then we want to look at percents. So limiting reactant is the reactant that is completely used up in the reaction. It's the one that's limiting the reaction. Okay, so that means I have the smaller number of moles of the limiting reactant. It's going to determine how much product can be produced. And of course, in that following reaction, the ethylene was the reactant. That was the limiting reactant, right? Because we had excess water. That means water would be the excess reactant. The reactant that has the amount left over at the end, that's going to be your excess. That means you have more moles than what you needed for the reaction. And again, in that example, that was the water. Now, limiting reactant calculations, you're going to do everything just like you did up till now. We'll write balanced equations, then we'll identify the limiting reagent, we'll calculate the amount of reactant B needed to react with reactant B. So now what we're going to do is we're going to do mass of A to moles of A, moles of A to moles of B, and then moles of B to mass of B. So it looks very much like we just did. Then what we're going to do is compare the amount of B you need with the amount of B you actually have. Okay? If you need more B than what you have, then B is the limiting reagent. If you have less than B, then A is the limiting reagent. So calculate the mass of desired product using the amount of limiting reagent and mole ratios. So how many grams of NO can form when 3 grams of ammonia and 40 grams of oxygen react according to this reaction? Okay, so step 1, we're going to take the mass of ammonia, turn it to moles of ammonia to moles of oxygen to mass of oxygen. Okay, does that make sense? They gave us two masses. They gave us 30 grams of ammonia, 40 grams of oxygen. So now we're going to take 1 mole of ammonia. That's going to be 17.03 grams. 1 mole of oxygen, 32 grams. Again, coming from the periodic table. Then we're going to look at our mole ratio. We have 4 moles of ammonia to 5 moles of oxygen. So we're going to start with our 30 grams of ammonia. We're going to divide it by the molar mass of ammonia. Use the balanced chemical equation to convert that to moles of oxygen. And then we're going to multiply by the periodic table to get grams of oxygen. And according to the ammonia, we would need 70.5 grams of oxygen. So now here's the key. What does that tell us? I'm sure all of you were able to work right through this math without a problem. But at the end, do you understand what we have done? So up here we're told we have 40 grams. If we use up all 30, then that's going to require that we have 70 and a half. So step 2, mass of oxygen to moles of oxygen to moles of NO to mass of NO. Now remember, we want to know how many grams. We're using the oxygen as the limiting reagent because we have 40 grams. And if we want to use up all of the ammonia, we would have needed 70. That's how we know that the oxygen is the limiting reagent. Okay, so follow that again. I should go back maybe. So here when we have 70 grams, and here we only have 40, then at that point, we know that the oxygen is going to be the limiting reagent. If this worked out to be less, all right, so if we only needed 25 grams of oxygen, then we would have known the ammonia was going to be the limiting reagent. Once we determine which one's the limiting reagent, that's the one we're going to use to find the product. So how many grams of NO can form when 30 grams of ammonia and 40 grams of oxygen react according to that reaction? Well, now we know that the oxygen is the limiting reagent. So now we're going to take the oxygen and go to the nitrous oxide. So 1 mole of O2 would be 32 grams. 1 mole of NO is going to be 30.01 grams. The relationship from our balanced chemical equation is 5 to 4. So now we're going to start with 40 grams of oxygen. We're going to divide by the molar mass. Then we're going to multiply by our balanced chemical equation. And then we're going to multiply by the molar mass for the NO. At that point, we know we form 30 grams of NO, which means we can only form 30 grams of NO. So once we've made 30 grams of NO, we've now run out of oxygen. There is no more oxygen in there, and we're going to have excess ammonia. Now, if 18.1 grams of ammonia is reacted with 90.4 grams of copper oxide, what is the maximum amount of copper metal that can be formed? So here we're giving you a list of molar masses. Right? And so now you can try to work this through. Remember, it's still 3 steps. And then you're going to do 3 more steps. So the first thing we're going to do is figure out which one's the limiting reagent. So we can start with 18.1 grams of ammonia and go to 90.4 grams of copper oxide. And then if you're higher, then you know that the copper oxide is the limiting reagent. If it comes out lower, then you know the ammonia is the limiting reagent. Once you have your limiting reagent, you're going to do 3 steps and then finally go from your limiting reagent to copper metal. And after doing that, hopefully you come up with 72.2 grams. So again, you're going to take 18.1 grams You're going to divide that by the molar mass of the ammonia, use the relationship in the balanced chemical equation, and then multiply by the molar mass of the CuO. And this says you're going to need 127 grams of CuO, but you only have 90.4. So the 90.4 is going to be our limiting reagent. Now we're going to divide that by the 79.55. It's a 3 to 3 for our balanced chemical equation, and our molar mass for copper is 63.546. At this point, we know we're going to make 72.2 grams of copper. All right, hopefully that went well. Again, if you need to watch it a couple of times, obviously pause, go back, watch it a couple of times. Do what you got to do. If it's still not making sense though, don't struggle with it. I don't want you spending like an hour watching this thing over and over and over again, hoping that it someday makes sense. If you're struggling after a couple of views, then make sure you come talk to me. All right, we can meet in a Zoom session. We can meet outside of those hours, or you can come into those hours. Okay, it's up to you, but make sure you get help that you need to get through these. Now, if 8.51 grams of C2H5SH reacts with 22.4 grams of oxygen, what is the maximum amount of sulfur dioxide that can form? And again, they've given us the molar masses and the balanced chemical equation. So I'll give you a pause here. All right, hopefully you came up with 8.77. So again, we're going to start with our C2H5SH, and we're going to compare that to the oxygen. So if you're still not sure why I'm comparing those two, remember these are the two that they've given us masses for. So we had this much of this one and this much of that one. And so we're going to figure out how much product we're going to make based on those two. So that's why we're competing those two together first. Once we do those two, that's going to tell us, after everything cancels out, how many grams were needed. So here we see we had 19.7 grams of oxygen are going to be needed based on the 8.5 grams of the C2H5SH. Now, in the question, we're told we have 22. So that means then the oxygen is going to be, oh my gosh. So we figured that the oxygen is 19.7 grams. We have 22. That means that this one's going to be the limiting reagent, right? So the 22.4 grams of that is limiting. So now we'll use the 8.51 grams of the C2H5SH, work through the same process, but now we're going to go to SO2 because we want to know how much sulfur dioxide are we going to form. And based on that, that's how we got the 8.77 grams. All right. So another long session, but I apologize for that. But again, we got into the middle of stoichiometry and we needed to get through it. So I'm going to pause here. The next segment will be our last segment where we're going to talk about reaction yields. And so percent yields is going to be the sort of the last piece that we need for the puzzle. And so you might need to go back and watch the stoichiometry stuff again and again until you get it down, because you want to have stoichiometry down moving forward. From here on out, the next few chapters, all we're going to do is change a few things about stoichiometry. And I mean change it, I don't mean change, I mean add to it. So we're going to start looking at how to predict products. And so you have to be able to do all of this stuff on top of that as well. So remember, chemistry is a building process. We started with atomic structure, then we went to naming, now we're going to reactions. In Chem 150, what we're going to do is spend a lot of time looking at reaction types and then looking at some of the details of it. So again, stay tuned for the next segment. It should be the final segment, and we'll finish off this chapter. All right.